This meeting is being recorded.
All right, welcome everyone. Today it's our great pleasure to have Sacha Ikonicoff from the University of Ottawa, who will be telling us about Quillen-Barr-Beck cohomology of divided power algebras over an operator. Take it away.
Thank you. So indeed, I'm going to talk about this program that I started a while ago with Martin Franklin, who is right here, and Yannis Doukas, who is from the University of Athens in Greece. So very quickly, what my program is going to be for today, I'm going to do a quick recap on Quillen cohomology in general, but I've understood that there's already been a talk by Martin recently about that, so I'll go fairly quickly about it. And then I'll move to the case of operas, and perhaps I'll spend a bit more time on what happens for Quillen cohomology of algebras over an opera. And then towards the end, I'll be able to add divided power structures, which is really the new stuff, the thing that we did with Martin and Yannis. So let's dive into it. So Quillen cohomology, we always start with a category that has at least small limits. And if you fix an object A in that category, what I'm going to call a Beck module over that object A is an abelian group object in the slice category over A. And the general idea is to obtain the cohomology theory from these Beck modules. And the cohomology will have coefficient in these Beck modules. So if right now you have no idea what I'm talking about when I'm talking about these abelian group objects in a slice category and want to call them modules, well, here is an example. In commutative rings, there is indeed an equivalence of categories between those Beck modules over an object A and actual bimodules over the commutative ring A. And that equivalence of categories is given on one hand by taking a Beck module and associated to it its kernel, and on the other side by taking a bimodule M and sending back what we call the semi-direct product. So the semi-direct product of A by one of its module M is given by the direct sum of A and M, and then the ring multiplication in it is given by, well, if you take two elements, AM and A prime, M prime, you multiply them together, what you get is AA prime in the A component, and then in the M component, you get A applied to M prime plus A prime applied to M. You see that this kind of like crossing multiplication. And that's a phenomenon that we'll see again.
The E doesn't act on the other side, A prime?
What do you mean?
Like it's not A M prime plus M A prime?
No. So yes. So here, the A never acts on M, and A prime never acts on M prime.
No, he meant that it's in commutative rings, so it doesn't matter how you write the action. There's only
yes,
one action.
It doesn't matter in which way I write the action because I'm considering bimodules in which I say the two actions are the same. All right. And so how do I get a cohomology from that? Well, we start by studying that forgetful functor that takes a Beck A module. And again, that was an abelian object, abelian group object in a slice category. So we can forget the fact that it was an abelian group object and get an object in the slice category. So this kind of like forgets a part of the structure. And if this functor admits a left adjoint, then this left adjoint is what we call the abelianization functor and denoted by ab of A. So to come back to our example of commutative rings, if you compose that with the equivalence of categories given by that semi-direct product, what we're really looking for is a left adjoint to the functor that takes an A module and sends it back the semi-direct product of A by this module as an object in the slice category over A. All right, and so after a bit of standard construction, what we find is that the abelianization of an object B over A is going to be given by the free A module generated by what we call the Kähler differentials of B. All right, so again, how do we get a cohomology from that? If the category C was nice enough, and if you wonder what nice enough means, you can ask Martin, for example. Then when you pass to the simplicial objects in Beck modules and in the slice category, the left-right adjunction between abelianization and the forgetful functor is in fact a Quillen pair for what we call the Quillen model structure. And so we're going to try and derive that left adjunct functor, the abelianization. And so if we have a cofibrant replacement AC for A, we can apply that left derived functor to the cotangent, we can apply that abelianization functor to the cofibrant replacement, and what we get is what we call the left-derived functor of the abelianization, and that's what we call the cotangent complex. So the Quillen homology for A is going to be the homotopy of that simplicial object, and the Quillen cohomology for A with coefficient in the Beck module M is going to be the cohomotopy of a co-simplicial object that's given by looking at the maps in A Beck modules from the cotangent complex into M. So that was a quick dive into Quillen cohomology. My point was mainly to do some recap, and I'll summarize what we've seen just here by this little table. In a general category C, we define Beck A modules, and that in commutative ring correspond to A module. That's this adjunction between the kernel and the semi-direct product. This category of A module is presented by an algebra. In this case, it's just A, so I didn't need to construct a special algebra that represent these modules, but we'll see later that we'll need to do that in a more general case. And then we're interested in a notion of derivation defined by Beck, which give us the algebraic derivation in rings, and then a representative for this derivation is given by the Kähler differentials. Once we've defined all those characters, we can build the cotangent complex for Quillen cohomology. So that's the idea, the general idea of the program, and our point is going to be to do that, starting with operads. So first, let's define what an operad is.
So sorry, you're trying
Yeah.
to do this for Beck modules?
I'm going to do that for Beck modules over a category of algebra. And in particular, I'll do it for a category of algebras over an operad. Beck modules are defined in any category that has small limits. So I can select my favorite category of algebra and apply the Beck program. That's what I'll be doing with algebras over an operad. Right. So I'm going to fix a field here, F. Everything that I say about operad can be done over for operads over a ring and modules over a ring. But because I want divided powers later, I can right off the bat fix a field, because for divided powers, one really needs a field.
Oh, sorry,
Yes.
the full screen mode, I think. You'll get under view in the menu.
Oh yeah, of course. If that's a bit
Full
bigger,
screen mode, yeah, right there.
just yeah, but I don't like that.
Oh, it's actually worse. Yeah. Yeah. It's nice. Okay, fair enough.
No, but I like how to make it in a. It has to be display in a thing, but maybe read mode is the right one. Yes. All right. So let me describe what an operad is over a field F. It's a sequence P, which is given by, for every integer n, vector space Pn equipped with a linear action of the symmetric group on n letters. And what I really want you to imagine is that this vector space Pn is in fact a space of operations. So to do that, first I'm going to give you a graphical interpretation. When I have an element mu inside Pn, I'll generally think of it as a sort of corolla with that index mu for the name of the element, and then n input on that corolla. And to really be able to call that an operation, well, I need to look at what someone can do with an operation. And the two things that I really want to do is compose operations and permute the inputs. So first, to permute the inputs, I gave an example here. Pn is always equipped with an action of the symmetric group on n letter. And so if I have, for example, the transposition of 1 and 2, I'm allowed to apply that transposition to an operation mu. And you have to think about it as twisting the two first inputs. And of course, in general, if you have a permutation sigma, you have to think it as permuting the inputs of your operation accordingly. So that's for the permutation of input. But I said that I also wanted composition. So imagine that you have an operation mu with arity n, and then operation nu1, nu2, etc., up to nu n. I want to be able to say what happens when I take my operation mu, and on each of the inputs, I plug a new operation ui. So it means that I have an operation that takes an element mu in my operad of arity n, elements in my operad of whatever arity, and gives back an operation in the operad, which has arity, well, the arity of nu1 plus, etc., plus the arity of nu1.
Sorry, Sacha. I find that keeping track of all sign conventions is a nightmare.
Yeah.
And I'm used to the sign convention where Pn has a right gamma n action.
Yes.
Are you using a left gamma n action there?
Yes. So I never choose because I hate choosing. And so, in this case, let's say they won't matter for what we're going to do.
Okay, fair
But
enough.
indeed, in the usual convention, the action is on the right, but it can also be written on the left, depending on if you're talking about permuting input or permuting the place of elements. And so this composition has a unit 1p, which is a corolla of input 1, which you have to think of as, well, if I compose 1p with mu, or if I compose mu with 1p on the top, nothing happens. The element that I get at the end is mu again. So this has to satisfy certain relation, like associativity, that tells you that no matter in which order you're going to compose your trees, you're always going to get back the same operation. Unitarity is what I said just here between the unit and any other elements. And equivariance tells you what happens if I'm composing those operation like here, and then I try to permute the inputs, or the contrary. If I permuted the inputs in mu and then composed, then I need to have some sort of relation that tells me that that corresponds to what I'm expecting to happen. All right, so we care about operads because they, in fact, give us categories of algebras. The fact is, if I start with an operad P, I get a vector space SP that sends a vector V to that thing here, which is the direct sum over all integers of the space of operation of arity n, tensored with n copies of V, and then I have to mod out by the action of the symmetric group. So to think about an element in this particular summand is to think of an operation of arity n, and then n elements inside V, and vectors, which I consider as putting actual inputs in my operation. And then the permutation tells you, well, again, we come back to that question of notation between the left and the right. This is probably incorrect, and I don't really care for this particular talk. This functor here has a structure of monad, which is precisely given by the composition and unit that I described on operads. And what we call an algebra over the operad is just an algebra over this monad. So really, if you remember what an algebra over a monad is, it gives you a map from SPA into A, and you have to see that as actually taking an operation mu and applying it to n elements in A. So let's see some examples. We usually don't think about, or we can talk about a lot of different types of operads, but of course, the first examples correspond to algebras that we're used to working with. So there's an operad that we did not ask for associative algebras, and then this monad just becomes the tensor algebra. And similarly, there's an operad for commutative algebras for which the monad is the symmetric algebra. And then there's an operad for Lie algebras, for Poisson algebras, etc. Now we're going to make some Quillen cohomology. So just like in the first section, we're going to fix a p-algebra A and start to think about its Beck modules. So let B to A be a Beck A module. Because it's supposed to be an abelian group object in the slice category, what we get, just like in the classical case, is a short exact sequence in vector spaces of that form. So here the projection is a map of p-algebra. It has a section, and we're interested in the object M, which is the kernel of that map. I see a typo right here because it's ker P, it should be ker PR. So because in vector spaces we can split that sequence, it means that B is linearly isomorphic to the direct sum of A with M. So again, we're going to think of elements of B as a couple, an element of A and an element of the kernel. Now the question is, what should the algebra structure on B look like? So to find that, we have to use the usual computation, and here is how it looks. Since the projection onto A is a p-algebra morphism, that tells us that applying an operation of arity n on n couples A1, M1, etc., AN, MN should look like, on the first component, the operation mu applied to A1 to AN, and then we don't really know yet what happens on the second component. So that second component that we don't know yet, we're going to call it phi mu of, and then all the inputs that we had. So A1 to AN and M1 to MN. We do the usual standard computation, for example, using that the addition inside B is supposed to be a map of p-algebras. And after a while, what we get is something like phi mu of A1AN M1MN is equal to a certain sum where one of the inputs in A is 0, and all the inputs in M are 0 except for M. And now this one summand of the sum, I want to consider that as a certain module structure of A acting on the kernel. So I'm going to define this thing, which applies an operation of arity n, mu, to only inputs in A except for one, which is in the kernel. And that's just a definition so far. But we can then define an A module as being precisely a vector space equipped with operation of that form that satisfy a certain associativity. So here's the definition. An A module is a vector space M equipped with a map of that form, which precisely tells you that when you have an operation of arity n minus one elements in A and n elements in M, you can send back an element in M. And what's missing there is, of course, it has to satisfy a certain associativity. And the equivariance is already encoded in that sigma n here. And the proposition then becomes that if you now take the direct sum of A by M, you can give a p-algebra structure on this direct sum, and it's going to be given by, when you want to apply an operation of arity n mu on n couples, A1, M1 up until A and Mn, well, the first one, you're going to apply mu to only things in A, and for the second one, you're going to sum all the possible ways of having the operation mu applied to n minus one elements in A, keeping the order, and just replacing the ith one with n. And I see another typo, which is quite important. Here, it should be mi. It's only the element mi that we're introducing here. So that particular p-algebra structure on A plus M, we're going to denote it by the semi-direct product and call it the semi-direct product. The reason why we're doing that is that indeed, what we can prove then is that there is an equivalence of categories, just like in the commutative ring case, between Beck modules over p-algebra A and what I just defined as an A module, given by taking the kernel and giving the semi-direct product.
Sacha?
Yeah.
If I may chime in.
This description there is very pleasant. If we compare to what you said earlier about associative rings and bimodules, because then you think of mu equals just the multiplication in parity 2.
Yeah.
And then the only terms that matter will be those multiplication of A1, M2, that's the left action of A
Yes.
on M.
Yes,
And
exactly. So
M1, A2 will be the right action on M.
that's correct.
That's it.
If I do an example for the commutative algebra, all that matters is the operation of arity 2, and then I'll get just two couples, and what I'll get is A1, M1, A2, M2, and what I'll get here is A1, A2, and here I'll get A1, M2, and M1, A2, so in the wrong order, but because I'm in the commutative algebra, I'm allowed to change back. But if I look at associative algebra, then the two multiplication on the left and on the right are different, and this does keep track of that. So remember that now, if we want to make a Quillen-Cohomology out of that, we need to be able to find a left adjoint to a particular functor that takes a module over A and takes the semi-direct product of that module and forgets the Beck module structure, just remembers that you have an object in the slice category over A. If I find a left adjoint to that, that's what I'm going to call the abelianization functor. So in more details, what I mean is that I want to find a module over A that fits into this equation. So let's look at the morphism on that side. It's a map from B to A semi-direct M. So in particular, it's given by two maps, F1, which goes from B to A, and F2 that goes from B to M. And in order for this map F to be a morphism of P algebra that makes that triangle commute, I need first the fact that F1 is given by the same thing as the projection, and second, that F2 satisfies a certain relation which looks a lot like a derivation. And indeed, that's what we call an operatic derivation. So we want that F2 from B to M to satisfy the fact that if I apply F2 to an operation mu applied on n inputs in B, B1 to Bn, what I get at the end is the sum of all the possible ways of applying that operation mu to only things in A that are obtained by projecting onto A by the projection from B to A, except one where I'm going to apply that F2. And you can check that each of those summands, because everything is in A except for one which is in M, this whole thing is indeed in M. So now what I just said is that morphism from B to A semi-direct M is the same thing as derivation over A between B and M. So what I'm left with is trying to find a representative for that functor of derivation. And the definition will be just like in commutative rings. I want something that I call the Kähler differentials. And the Kähler differentials of B will be a module denoted by omega B. And it's the B module that is generated by symbols dB for all B in my algebra B, where D is linear. And I force that relation that if that D is in fact a derivation, so if I apply D to mu of B1 to Bn, that gives me the sum of all possible ways of having mu of all those BIs except one where I stick a D. All right. The important part is that, of course, I built the right thing so that omega B is indeed a co-representative of the functor that takes a module over B and gives back the derivation over B between B and N. But you might see a problem. The derivation between B and A, between B and M. But that's okay, because the only difference between those two things is that here we could consider M as being a module over B through the pullback of the projection. So we just need to apply the left adjoint to the pullback of the projection, which is just an extension of scalars. The problem is this extension of scalars, I haven't told you where it is. In particular, I haven't told you how to make a free module over a vector space. And so that's what I'll need to define here. So I just said exactly what I wrote here. So perhaps if I had shown that, that would be easier. The derivation between B and N are morphism between omega B and N, but B is a Beck module, so it's equipped with the morphism 2A. And that means that, in fact, those derivations that we were looking at were morphism in B modules between omega B and the pullback of M.
So B is an operator?
B is an algebra with the same operand as A. Here, I've fixed an operand P, I fixed an algebra A, and now I'm looking at a Beck module B over the algebra A. And so what we need is the free A module generated by omega B. And if you remember in commutative rings,
Can we go up the equation?
yes.
To pedantic here.
So this, which one?
Go up a little bit. That equation there.
Yes.
So under the relation, that is like your, what does that mean?
You'll have to repeat questions.
So-
I can't hear.
So the question was, what does that mean to be a B module generated by symbols under a certain relation? So in this case,
There's some kind of universal property it has with respect to that relation?
yes, what we want to do is to have something that co-represent omega B. So I could actually define omega B as just a co-representative and then show that naturally it satisfies this thing. But you can take that as, so a B module is a vector space with an action of B.
So your operands are in some fixed category?
My operands are in vector space over a field.
of vector space?
Yes. And so I'm looking at a B module, which is a vector space M with an action of B, which is defined by those mu applied to something. And I'm saying that on a certain set of symbols, dB, I can apply all the operations from B that I want. So mu, B1, etc., dBi up to Bn. And then I'm modding out by this relation, even in vector space, that's enough. Because that will conserve the action of B.
All the mu's are multilinear?
Yes, mu is always, the operations of an operand in vector space are always multilinear.
Right. So then,
Is that good?
yeah, kind of. Thanks.
And so if you remember in commutative rings, to take the free A module generated by something, I just had to tensor by A, and that worked. But in this case, that won't work because we have operations of possibly more than RT1. So tensoring doesn't necessarily have a structure of, like if I take A tensor over B omega B, that doesn't necessarily have a structure of A module, in fact. So instead, I'm going to look at the category of modules over A and observe that it's an abelian category that is sufficiently nice that I can actually define an associative algebra that will represent those modules. So let's think about how to do that. A module over A is supposed to have an operation of the type, I take an operation in my operand of Rtn, and then n-1 elements in A, and then I'm supposed to be able to plug things from the module and get back things inside the module. So it means that purely formally, the operations that define the category of A modules are precisely those symbols where I take a mu and then n-1 elements inside A, and I leave a placeholder which represents the place where I'm supposed to put the element in my module. Of course, all of that will be linear in mu and in all of the A's. Now, the universal enveloping algebra is going to be the algebra denoted by U of A, given by those symbols under certain relations, so the linearity that I just talked about for each of the inputs, and also the fact that if you take,
that symbol as a map is actually like an automorphism of A or an endomorphism of A?
no, it's not. It's an operation from M to M if M is a module. And if you have to think about those symbols here as operations on A modules. So for example, if I'm in commutative rings, these look like A applied to blank. And if I'm in associative rings, I have A applied to blank and blank on which acts A on the other side. Yes, there's another question?
Just a tiny one. So do you technically have like n+1 elements and then n+1? Or?
So no, that's just a question of conventions. Because I need to have at least one placeholder. So in this case, for example, I don't have the symbols in which mu are of arity 0, but that's a good question.
Oh.
And so the relations.
You're just writing these things up. This is just a symbol.
Yeah.
It's nothing else.
It's a symbol, and I'm just saying that it's just a symbol linear in mu and in A1, etc., etc. But to make that into a ring, that's what I'm about to explain.
But I mean, when you say it's a symbol linear in things, I don't know.
Vector space generated by under linear.
So that's a basis.
So that's not a basis, that's a generating family in a ring, in a vector space. But then I'm saying that it's a ring, so I need to actually, I go back to read more. I need to actually define the multiplication. And the multiplication will tell me that if I take one symbol like that and then a second one, the multiplication of the two tells me what happens if I wanted to put the second one inside the placeholder of the first one. And the answer is, well, I'm supposed to take my operation mu, and then I'm composing here, so it means that my operation mu will be placed at the ith input of mu. And I didn't describe what a partial composition was earlier, so I'm going to do it now. It's like taking mu and then putting the unit everywhere except for the input I. And then at the input I put mu. And all I have to do is put my inputs in the same order as before, replacing the ith one by the input that were here. And still, I have one placeholder that appears in the composition. So one proposition on that is proving that this actually gives you an associative multiplication, but that is completely guaranteed by the associativity of the composition in the operand. So in the end, I get an algebra U of A, which is associative, and we'll see that this represents modules.
It doesn't seem like this depends on A, though, if you're just taking symbols.
Well, it does, because I'm actually composing here and applying that operation, which actually has a reaction with what happened in A. For example, I could replace A1 by, perhaps I forgot to denote one relation. You're right in that sense, is that if I take one of those A, for example, A1, and I replace by itself an operation on elements in A, I'm again allowed to compose the operations in the right way. And so that means that the structure of A algebra on A corresponds to that multiplication. So I give an example that might help. Yeah.
You talked about a shuffle map in the first talk.
There's no shuffle here. There's no shuffle at all. So I'll give an example. If you take a Lie algebra G, the universal enveloping algebra in this sense of G is the same thing as the universal enveloping algebra that we know. If you compute what it gives you is the same thing as the tensor algebra over G, quotiented by the bracket of two elements is the same thing as the anti-commutator. Of course, that comes after a bit of computation. The commutator, indeed, not the anti-commutator.
Is that abelianized, the tensor algebra?
It's not abelianized.
Okay.
No. You want it to be associative, but you don't necessarily want it to be commutative. And the proposition is then that indeed I built the right thing. So U of A is the associative algebra which represents A modules. So the category of A modules is equivalent to the category of U of A left modules. And now I know how to create a free A modules. I just have to tensor by not A, but by this algebra here. And finally, I get the adjunction that I wanted. On one hand, from a module over A, I can take the semi-direct product. That gives me a P algebra over A. And on the other hand, I'm going to take the Kähler differential of algebra over A, and then tensoring it with this universal algebra, what I get is the abelianization functor. So now the question is, do I get interesting cohomology on categories of algebra with this? So if you left derive that particular functor, in the case of associative algebra, what you get back is Hochschild cohomology. If you do that with commutative algebras in characteristic 0, you get what we call Harrison cohomology, which is a bit finer than Hochschild cohomology because it takes into account the fact that, well, it doesn't expect things to be commutative to start with. If you do that on Lie algebras, what you get is the same thing as Chevalley-Eilenberg cohomology, etc. So indeed, this construction gives you a general way of building cohomologies on categories of algebra. All right. Is anybody happy so far?
Tiny question.
Yeah.
So the other, like the Hochschild and the Chevalley-Eilenberg, those are not characteristic 0?
They're in general, whether the characteristic is 0 or not does not matter. But Harrison cohomology is only defined in characteristic 0, is what I'm saying.
Oh, okay. Yeah. Okay.
I had a question.
Yes.
So this left adjoint, the existence of this left adjoint is a necessary and sufficient condition for Quillen cohomology to be defined on these categories. Is that correct?
So when you have a left, what Quillen cohomology says, it just says, if you have a left adjoint to a Bayesization and the category that you started with is nice enough, and the nice enough I put under the rug on purpose, then what Quillen says is first, on the simplicial version of that, you have a Quillen pair, and because of that, you're allowed to left derive your Bayesization. So if you start with something that is not too bad, and in this case, I'm starting with algebras over an operad, which have all the things that we want. They're co-complete, they're complete, they have all those things. Then necessarily the simplicial version of those functors will be a Quillen pair. So you'll be allowed to derive on the left, etc.
Okay,
Right?
thank you.
Thank you. So now I've done all that program with operads and algebras over an operad, but that's very well known. This dates back to articles published in 2000 by Gerson Hopkins. I want to do the same thing, but not with operads and their algebras, but with operads and their divided power algebras. So let's look at what a divided power algebra is. And for this, we're going to fix the characteristic of our base field to be a prime positive number. Because if your characteristic is 0, divided power algebras are just the same thing as algebras, so we don't really care about what happens in this case. So I fix my characteristic to be a positive number. And the first proposition is that if my operad does not have arity 0 operation, which are non-trivial, then there exists a monad structure on that other functor, which is defined just as the one before, except that instead of modding out by the action of the symmetric group like earlier, I'm taking the submodule of invariance under this action. And if I have a monad, of course, I have a category of algebras, and that's what we call divided power algebras. So I need to straight away give you an example, otherwise you won't see why I care about this kind of algebras. So if I replace my operad by the operad of commutative algebras, what I get is a notion that is a commutative algebra plus an operation gamma p that represents, in a certain sense, the operation that sends an element a to the power p divided by p factorial, knowing that this doesn't really make sense since I'm in characteristic p. And the only three relation that it needs to satisfy is that first, this p power is monomial of degree p. So if lambda is a coefficient in your field, gamma p of lambda a is lambda to the p gamma p of a to the p is equal to 0. Why is that? Well, because if you look at this false equation there, the one that becomes true is if you multiply by p factorial and you get p factorial times gamma p of a is equal to a to the p, but p factorial is equal to 0. So indeed, a to the p is equal to 0. And finally, you have a sort of modified Newton formula for gamma p of the sum. Anyway, again, you might ask me why I care about this kind of algebras. but these are what we call the classical divided power algebras. They were defined by Kähler in the 50s and then appeared in crystalline cohomology, deformation theory, etc. And if instead I replaced my operad by the operad of Lie algebras, what I get is something which is called a restricted Lie algebra, which has been studied in depth by Nathan Jacobson even in the 40s, and showing that this is the right notion of Lie algebras in a certain sense in positive characteristics. All right, so the first lemma is how to compare a divided power algebra to a natural, usual algebra as we know. Well, if you look at the trace morphism which exists on every representation of a group G, well, this trace map will give you a way of building a monad morphism between the usual monad induced by an operad and that new divided monad gamma p. So the first theorem is how to characterize those divided powers, and that's a theorem that was in my first article. And it says that a gamma p algebra is the same thing as a vector space equipped with certain monomial operation. So let me just give you a way of bookkeeping this operation. Every time you take an RETN operation X, and then a partition R1 plus etc. plus RS of this RETN, that will give you an operation, and the RET is the number of integer in that partition. But now, when I say operation, they're no longer multilinear. In particular, they satisfy a lot of relation, but the one that shows you the nonlinearity is the following one. In fact, the ith entry is of RET Ri. And there's other relations, but they're very long, and I decide to not show them for this time, because the point is to talk about Quillen cohomology. All right, so just a note. If you look at what the trace looks like, it looks like taking an operation and acting on A1 to AN is the same thing as looking at this particular operation, which is beta, my operation mu, and then my partition will be a discrete one. So if you have a discrete partition, it's like applying an operation from the operad, and you can see from the relation above that this is indeed, well, it's monomial of degree 1 everywhere, but the other relation on the sum will tell you that it's actually linear in each variable. So in order to do Quillen cohomology, what do? We fix a divided power algebra, which is a gamma p algebra, and then we're going to start looking at the Beck models.
Sorry, Sacha.
Yeah.
In the example of com,
yeah,
can we see that operation gamma p in that notation?
Yes, that's actually a good idea. So I'm going to try and write on the board where they can see.
There should be only one block, and it's just p. Is that it?
If you take x2, well, xn to be the generator of the RETN elements in com, I'm just going to tell you that it's always dimension 1, so there's only one. I don't know if it's very visible, but we'll see. If you take xn to be that generator, then the gamma p applied to A is the same thing as taking beta xp, where you take everything together p, so that's a partition of length 1 applied to A. And again, if you look at what I wrote earlier, multiplying two elements, that's something that comes from the operad, which tells you that you should have a discrete partition, and this is how it looks. And the relations will tell you that this is indeed commutative, etc., etc. It comes from the operad. Right. Is there any other question while I'm there? So let's start building up to our Quillen cohomology. I'm going to straight away define the notion of a module, which of course is supposed to give me my Beck module. And if I think about something that makes sense, earlier we had operation where we put all the inputs in A except for one. I'm going to do the same. An A module is a vector space M, which has additional operation every time I take an operation in my operad and a partition R bar, and I put all the inputs inside A except one that I put in M, then this should be an element in M again. And it turns out that this definition is the right one. So there's a couple of relations that this has to satisfy again, but maybe one or two that are quite satisfying to see is that it turns out that those operations, there's a bit to prove before you can get there, but they are additive in the entry in the module, but they're not linear in that entry. They are in fact linear by, they are in fact monomial of a degree Ri being the partition, and I can even prove that I can replace this Ri by a certain power of P, which means that those operations are necessarily P to the K, semi-linear for a certain K. So for example, if you take P to become the operator of commutative algebra, an A module is the same thing as an A module in the usual sense, plus a P semilinear map from M to M, such that that semilinear map, if it's acting on an element on which an element of A is already acting, then this is supposed to be 0. So now we need a notion of a derivative, of a derivation. And in literature, there was already a notion of derivations for divided power algebras. It was something from a divided power algebra B into a module M, such that this derivation applied to gamma P of B was equal to minus B to the P minus 1 dB. So since this is already in literature, let's take it as a definition. It turns out this is not the right notion of a Beck module, because what we forgot here is that M itself had a sort of gamma P, and we need to just add what that gamma P does inside M. That gamma P in M is the map that I called pi here. And so the right notion is this one. You have that relation instead, where I just added pi of dB. Now, how to call that, since the first one was a special derivation, maybe I can call it a very special derivation. We don't have a good term apart from calling it a Beck derivation, since it turns out that it corresponds to Beck derivations. And now the other definition that I need is how to create a semi-direct product. So again, I take my algebra A and my A module M, I take the direct sum, and then I ask you how to make a divided power structure on that. And you might think that if I apply my operation X, R1, Rs to those couple, I'm going to, on the first component, on the A component, apply that same operation to all the things in A, and you would be correct to do that. And on the other, on the M component, you might say, well, I just need to replace one of the A's by an M, and there you would be wrong. The actual right thing to write is this. So I'm just noting here that I forgot the component in A here. But as you guessed, it's the operation applied to A1 to AS. But for the second one, I'm in fact going to sum over all the ways to first pick an input between 1 and S, and second, split the monomial degree, Ri, into two integers, J and K, such that the K must be strictly positive. And then I'm going to leave my AI. It's still going to appear here. And because I've split that integer, I now have one extra input, so I can, on top of that, add my M. And I just have to withdraw what I just said. This definition is actually correct, because if you add the parts where K is equal to 0, you're actually adding what happens for when you apply this operation to all the A's below. In any case, the first proof is proving that this thing actually gives you a gamma P algebra structure on A plus M, and that's perhaps the long proof. And the next thing will be to show that this is the right notion of semi-direct product. Here is the theorem due to Yanis, Martin, and myself. There is an equivalence of categories between Beck modules over A and A modules as we defined it ourselves, given by taking the kernel and giving that semi-direct product. All right, is everybody okay to that? Okay, so we're approaching the goal. Now the goal is to look for a left adjoint to that semi-direct product with image not in Beck modules, but just in the slice category, just like before. And for that, we need a representative for the derivations and a representative for the modules. So for the representative for the derivation, we're just going to do the same formal thing as before. We take the module of Kähler differentials of B to be what we denote omega B, and it's the B module generated again by symbols dB for B and B with D linear under a relation that just says D is a derivation. Of course, the proposition will be that omega B does co-represent the functor of derivations. And again, now we need the free A module generated by omega B, and that's going to be just a tiny bit more difficult than before. So we need the free A module generated by omega B, and for that, just like before, we have to find a universal enveloping algebra of A in the sense that this universal enveloping algebra U of A will be an associative algebra such that the left modules are the same thing as an A algebra. And again, it's going to be like before. We're going to generate that by symbols where we take all the possible operations with everything in A except for one input that we replace by a placeholder.
Time to conclude soon.
And okay, and it satisfies a bunch of relation. So there's an example for that given by Docas, that in the case com, you're just taking your algebra and you tensor it by a polynomial algebra where the generator, you have to think of it as the gamma p with a placeholder inside. I'm going to skip on that because I want to talk a bit about comparison. All right. So the proposition is that indeed that U of A is the right universal enveloping algebra. And so the following theorem is that we get an adjunction where the free A module over the Kähler differential of blank is exactly the Abelianization functor. So from that, we have an available Quillen cohomology for divided power algebra, and you might wonder how this compares to the Quillen cohomologies they talked about earlier from algebras, and that's what we're going to do. So again, earlier I said there was a monad morphism which is given by the trace, and that gives you kind of a forgetful functor, the pullback by the trace, which forgets the divided power and just takes back the P algebra structure. And in the other sense, there's a push forwards that take a P algebra and associate formal divided powers on it. This induces, in particular, a map theta from the universal enveloping algebra of the pullback of A into the universal enveloping algebra of A. And we get a first commuting diagram of adjunction, where the horizontal adjunction are the Abelianization, and the vertical ones are given by this trace. And the proposition that we got first is that
I can't hear the speaker anymore, nor see the slides.
Sorry, can everyone still hear? Or
No, I cannot hear the speaker anymore, and I can't see the slides either.
the slides are not showing, right?
Yeah.
Yep. Just a sec.
okay, we're almost back. So let's go So now you have to cut your sound. All right. So if you can hear me, I'll finish quickly. So what I was saying is that with that adjunction, I can get comparison maps using a result of Martin, which goes from the Quillen homology of the pullback of A into the push forward of the Quillen homology in A, and from the Quillen cohomology of A with coefficient in M to the Quillen cohomology of the pullback of A in the pullback of M. And we can even go a tiny bit further and using functoriality to create other comparison. So every time you have a morphism of operad from P to Q, this induces, just like with rings, a restriction of scalar and extension of scalar adjunction. And we again get a diagram of commuting adjunctions, where the horizontal maps are the urbanization and the vertical maps are these extension restriction of scalars. And I just want to show you one example. If you have a function, sorry, there is a morphism from the operad Li into the operad as of associative algebras, which is given by taking the bracket and representing it as the commutator in associative algebra. So the pullback along that is exactly the same thing as taking an associative algebra and looking at it as a Lie algebra, such that the bracket is that commutator. Now, it turns out that, in fact, divided power algebras over AS is the same thing as just associative algebra. And so the particular result that we obtain in this case is that for a module over the restricted universal enveloping algebra of a restricted Lie algebra G, there is an isomorphism between Hochschild cohomology of that restricted universal enveloping algebra with coefficient in M.
Maybe up to a shift.
And yes, and Quillen cohomology of that restricted algebra G, the new cohomology that we created with coefficient in the pullback of M. But as Martin said, this is actually up to a shift and a small change in degree 0. Well, that's all I had to say for today. So thank you very much. And hopefully I'll be back in Regina one day.
All right, let's thank our speaker.
Are there any questions for Sacha?
Martin asked if there's any question for me. You can post them in the chat or unmute yourself, as easier.
Well, I've asked a few throughout the talk. So.
Already got a couple during the talk, indeed. So perhaps nobody has question anymore.
All right. Then, if not, let's thank Sacha again. Thank you all for coming, and you have a good week. Take care.
Thank you very much.